Good morning, or good afternoon, or good night. Whatever the case may be when this video finds you, this kind of goes along day 1, day 2, day 3. This topic, as fundamental as it is, as basic as it is, it's very difficult because you have to use an amount of your imagination. We're talking about things that are far too small to be seen with the naked eye. We're talking about things that are far too small to be seen with a microscope. What we are talking about this week is the nature of matter and fundamentally what makes up that basic unit of matter, which is, of course, the atom. You learned yesterday. Everything I talk about in this next probably 15 minutes, you've already seen to some extent yesterday. This is just meant to be a repetition, but also maybe I'll say something that'll hopefully make something you read yesterday make more sense. Or you'll go back to yesterday's lessons and you'll see those again. And now you'll know how to play with that PHET diagram, the PHET on the edge elastic, or in the reading or the questions. Go through it slowly. This can be difficult because, again, the vast majority of scientists haven't even seen these things. This is something, atoms, that have been thought of to exist since times of Aristotle. Even in the Bible, they're referenced. Aristotle said everything we can see, right, and feel and touch is made up of smaller things. What those things were, he did not know. He was philosophizing about it. But if we could see a thing, he proposed, one of the first ones who scientifically proposed that there must be something even smaller that makes up that bigger thing. So that was pretty cool. The Bible says as well, for the things which we do see are not made of things which we can see. For the visible things of this world are made by invisible things. Atoms are definitely invisible. But yet we have a whole classification. They're organized in a periodic table, beautiful form. How do we know these things? Trust me, I would love to go into the history. I have a whole PowerPoint on the history of chemistry and how we got to the knowledge we do today. You are just going to get some names and some of the models in history, and we're going to do a real drive-by. We're going to just fast forward to what we know today. Okay, so with that, I'll read this. Each element, we're not talking about earth, wind, and fire, and water. What we now know scientifically as an element is chemically unique. Gold will always look yellow. Gold will always be soft. Gold will look the same in the shape and form of, not shape, but it's malleable. An earring as it would in the ground as a rock. All the particles that make up gold, that make gold gold, okay, the atoms of gold are identical. Again, whether a rock, a mountain, or an earring on your ear. Okay, every nickel made of nickel has the same particle. It's a pure substance. That's what an element is. To understand why they are unique, you need to know the structure of the atom, and that is the smallest particle of an element. Are there smaller things than an atom in the universe? Well, if we hold to the two things that we just spoke about of Aristotle and even in the Bible, then yeah. And it is true. We have found that there are particles that are smaller than the atom, but they do not themselves make up anything. So the atom then is the basic structural unit. There are subatomic, that is, particles smaller than the atom that make up the atom, but in and of themselves do and form nothing. It's not until you have the atom that you have any form or shape of matter. All right, so I'm going to go on to the next slides, and I'm going to remove my pictures. Models of the atom. All right, so what we're going through right here is a progression that goes back as early as 400 BC that something existed. We kind of imagine that to be a sphere. But really, it was Dalton who came up with the first model that gave it any real shape with scientific evidence and proof. Dalton's name is brought up multiple times, as we even call the weight of an atom a Dalton. We've gone away from the Dalton, and now we call it an atomic mass unit, or AMU. But Dalton or atomic mass units are interchangeable. You probably should know both because you would run into both. In reality, they're used about equal. But that was in 1803. So jumping into Thomson's plum pudding model, the idea here is you have a pudding. It's amorphic mass with like raisins or chocolate chips scattered on and through it. And so what we have here is we knew by the way it behaved that there was a positivity to atoms. And that's about the only thing. And that there was some other particle that might have held those protons together, because protons, or what they called protons at that time, were just positive charges. But you can see this positive field is difficult. Rutherford's model said, no, yes, there are positive charges, but they're all located centrally in something called the nucleus. And it is surrounded by something else. And well, that was, as you can see, about 12 years later, Rutherford's model. Sure enough, he said, if there are positive particles, then there must be a negative particle. And he discovered electrons. He did this by shooting them at a foil, kind of a gold foil. And there's just one of a few things that could happen with foil. You can either go right through it, it can deflect in another direction, or it can bounce right back at the source of the particle or beam. We'll just call it a beam of particles. You can go right through it, or you're shooting it. It can deflect, bounce off, or it can reflect right back at you, or it can be absorbed. And as we'll see in the next slide, that's what happened. And some of his experiments proved that there were electrons, what he called electrons, negative charges. So we have this unsure size, unsure shape, but we knew there was some positive charge to it, and we knew there was some negative charge to it. We did not know where they were in relation to each other until about 1913. And this is the model we use today because it's the easiest and most accurate to represent, although it's probably not exactly right. And science models are always being changed and updated as more information comes in. As you can see here, the charged cloud model is probably the most accurate, but it's going to be very difficult to work with that. And in principle, we're not wrong to say that protons are here in the middle with the neutrons, and the electrons are out here moving so fast you can't even see them. All you see is where they might be. Imagine those glow sticks that you just twirl around so fast they form this beautiful green or orange or pink circle, right? And you know, it's the glow stick making that light. But at any given time, where is that glow stick? Well, it's in that circle somewhere. It's making the circle. You're twirling it so fast. Electrons are high energy particles, negatively charged, high energy particles that are just flying around the nucleus, which is for the most part still. Now this picture is not to scale. Remember, this is a representation. So electrons are not that big compared to the nucleus. The nucleus is much larger than the electrons are. And the electrons are really way, way far out. I heard an analogy once that, or actually I read it in a text, that if you blew up the nucleus of an atom to be the size of a pea or a bumblebee, put on the 50-yard line at Texas Stadium, the first electrons would be on the outer edges of the parking lot. Meaning that the atom is mostly space. There's a lot of space between the nucleus and the electron. So if ever any two atoms come in close proximity to each other, and we know they do, the nuclei will hardly ever come into contact. It'll always be the electrons that are interacting, and we'll see how important that is later. So in science, a wrong theory can be valuable and better than no theory at all. We were able to build on each of these models to get to where we are today. And this is more or less where we are. This is the Bohr model of 1913, and it represents quite fine, and this one more to scale, how protons and neutrons are in the center and electrons are buzzing and flying about here in orbitals. So this is what you should have seen yesterday. You want to write this chart down if you haven't. I would definitely have written it down in lecture. And that is that electrons have a negative charge and practically no mass compared to protons and neutrons. They're about 4,000 times smaller. So Dalton was the first one who came up with the mass. They're too small to weigh. To give you an example, have you ever, and I'm sure you haven't, but if you've ever tried to measure the thickness of a piece of paper, for the most part, that paper's thinner than the black lines on that ruler. So how could you ever measure the width of a piece of paper? I'll let you think about that one. Well, what if you had 100 sheets of paper? Well, that you could probably measure with a ruler, right? And if it were 1 inch, then you know 100 sheets of paper were 1 inch, then one sheet of paper would be 1/100th of an inch, okay, or 0.01 inches. And that's the way that works. I know that's probably a little more math than you care to put your eyes around, but so we're talking about really small things, and Dalton was the one who said, okay, fine, you know, we can't measure, but we can measure a whole bunch of it. And he found that each proton weighs about 1 atomic mass unit, or 1 Dalton. And neutrons, although with no charge, they help to stabilize the protons and keep them in the middle. And they also are about the same size of 1 atomic mass unit. And they're in the nucleus. So all the mass of the nucleus, all the weight of the atom is right here in the nucleus. And so we call that the atomic mass. Is made up of protons and neutrons. We'll see all this again shortly. And the electrons adding practically no mass to the atom really just gives it more of the size. And when I say size, what I mean is in these orbitals out here, you still have some that are even further out. And so you might take up a lot of space because of the electrons, but all the weight and the mass come from protons and neutrons. So how did we get to that point of knowing there were more particles than just positive protons? This is a picture of Rutherford, and as we knew, or thought we knew, according to him, there must be something in the nucleus that keeps those protons together. You can figure this out as well. Think about 2 magnets. Now, if you've ever played with magnets, you know they come together, right? The opposite sides. But if you ever flip one magnet around and try to make it stick, you'll find that they always offset. You can never push it. It's just the craziest thing. Get any 2 magnets, try to pull them together, and the positive charges will repel each other. Like repels, opposites attract. So he thought, well, if there's a nucleus full of protons that are all positive, something's got to be there in the way or stabilizing it. Otherwise, these protons would go flying in opposite directions. And so what he did was he bombarded beryllium-9. So here's beryllium. 9 means it has at least 4 protons. 1, 2, 3, 4. And 5 neutrons, or at least the proposed neutrons. 1, 2, 3, 4, 5. This is all after the fact. And he bombarded with these alpha particles, aka helium, which has 2 protons and 2 neutrons for a total mass of 4. So when you add the protons plus the neutrons, you get the total weight. And that's what the larger number represents, is the mass. The smaller number is the atomic number, and that represents the number of protons. So when he combined these or smashed these together, all right, these electrons were emitted. Oh, come on, there we are. And so 4 plus 2 equals 6. And sure enough, he was able to form the element carbon. But when we look at carbon-12, and we see how stable it is, the mass, when he weighed it, kind of like that stack of papers, it was shy by 1 neutron per carbon. So in other words, carbon-12 has 6 protons, 1, 2, 3, 4, 5, 6, and 6 neutrons. 1, 2, 3, 4, 5, 6. And that helped to stabilize the protons and keep the nucleus together. But we're missing something, aren't we? 9 plus 4 equals 13. 9, 10, 11, 12, 13, right? So where did that last one go? That neutron shot off. Okay, so it was emitted. That's what we mean, but the neutron was emitted. So beware, if you've ever walked in the hospital radiology department and you see they're wearing those tags, they're picking up neutrons that are flying around because these neutrons are given off by elements and atoms in the environment, especially in a radioactive radiology department. So a neutron, a lone neutron, can be detected with our technology today, and it has no protons, so this is not an element. It's just a lone neutron that was emitted as a leftover. No need for it. Sayonara. See you later. So these are the subatomic particles, again, as you should have them written. I, in my models, always represent electrons with an E and a negative dash, a P with a plus sign, and an N with 0, or I don't even put a 0. I'll just put N. And again, you have the charges, 1, -1, +1, or nothing. And the relative masses, you don't have to memorize these, but we know, well, you do. You have to know that protons are 1 and neutrons are 1. If you ever want to know the atomic mass of an atom, all you got to do is count the number of protons and neutrons and add them together. That'll give you the total weight, because every proton weighs 1 and every neutron weighs 1. So you can always add those together. So these are big numbers in scientific notation, but all you got to note is that 24 to 28 is a 4,000 times difference. 10 times 10 times 10 times, or actually larger than that. Yeah. 4,000 times different. This is a good slide to go through. Working with information any way you can. So within atoms, we know there's a nucleus. The nucleus within it contains protons and neutrons. Protons are positively charged. You get that P, positive protons. Neutrons have no charge, neutral neutrons. I think of Jimmy Neutron. He was not quite that neutral. There are electrons, and electrons have a negative charge. Negative doesn't mean you're lacking, okay? Really, the terms positive and negative refer to the direction of their spin. They spin in opposite directions. So we can't really think of it in those terms, but it probably is easier to actually. So neutrons have no spin, positive spin, negative spin, or negative charge. So this is how we refer to the atom. This is the atom's identity, the number of protons. You'll be able to see this on the slides, but right here it's blocked off, I can see. So atomic number equals the number of protons. Generally, in their native and natural state of an atom, the proton number is equal to the electron number. Okay, so if you know the number of protons, you know the number of electrons. Well, that should be easy again if you remember that we define the atom by the number of protons. And right away that tells us as well the number of electrons. All right, we're going to go ahead and look at this last slide before I sign off. Counting the pieces. So this is what it might look like, carbon 12 versus carbon 14. We just saw this in the last example of bombardment. What's the difference? They're both got 6 protons. And because they each have the same number of protons, and proton is what we define that element as, carbon. What's different between carbon 12 and carbon 14? The number of neutrons in that element. So that's a heavier element. We call that an isotope. There'll be more about that early next week. So counting the pieces. Atomic number is the number of protons and determines the kind of atom. That number never changes. Atomic number is the number of electrons in a neutral atom as well. Neutral being key. Number of electrons can change, but for right now in the native state, we'll find that they're equal. Mass number, or atomic mass, is the number of protons plus the number of neutrons, which is what these larger numbers represent. So you can see that if you simply take the mass number minus the atomic number, you'll be left with, that's right, the number of neutrons. Atomic number is the number of protons. So atomic mass is protons and neutrons. So if you just subtract the atomic number from the mass number, you're left with the number of neutrons. All right. So it just kind of repeated some things you hopefully saw in your readings yesterday. I'm sure there are more professional videos done out there. I know I've posted a few, and you'll have an opportunity to watch a few more. We will begin to talk about the structure of atoms in reference to the organization of the periodic table here tomorrow.